Hello everybody and welcome to the presentation of the work I have done on facial key point detection and emotion recognition as a part of my course project EEL-6825 pattern recognition. But before that, let me introduce myself. I am Nishant Agarwal, a graduate student here at University of Florida. Let's begin. Let's first outline the different topics that we will be covering in this presentation. First, we will briefly describe the problem statement and discuss about the various applications of emotion recognition. Secondly, we'll state out some of the different approaches that has been proposed by different researchers. We'll stress upon the model that I have implemented with the use of transfer learning. Then we would also move on to the results that has been obtained from the various models and make a quick comparison between them. Finally, we will go through the demo and finish off with the conclusion. Emotion detection is one of the most important cognitive functions that our brain performs efficiently. A challenging problem of automatic recognition of human affect has become a research field involving more and more scientists specializing in different areas such as artificial intelligence, computer vision. Emotion recognition has its applications in education and gaming as well. For instance, a negative emotional state is not good for the learning process, whereas a positive mood can foster critical thinking and are appropriate for analytical tasks. Automatic emotion recognition algorithms can help to explore this phenomena by making assessments of learners' emotional states. Now, with the introduction of big data engineering and the availability of a large amount of customer information, ads can be displayed according to the user's profile. So adding information about the emotions of the users could provide more accurate personality models of the users. The problem statement in itself is quite complicated due to the presence of high variance in facial features, which differs from one individual to another, and even for a single individual there is a large amount of variation due to size, position and illumination conditions in the images. The problem can be categorized into two phases. The phase 1, which is the feature extraction phase, wherein we detect the key facial points. The phase 2 is the classification phase, in which we classify the image into these 7 emotion categories. Let's move on to some of the existing approaches in this emotion recognition field. The first one being the SVM classifier. So here, given an input image, the solution localizes the face region, and from this region they find regions of facial patches such as eyes and lips, and from the patches which have the most variance between two images, the features are extracted. Now these are then provided to the SVM. To evaluate the method, a 10-fold cross-validation is applied. Second, combining the auditory and the visual reception and using this multimodal information in detecting the correct emotional states are quite promising. Researchers have also proposed another architecture, which is a 27-layered neural network. This network is trained using the stochastic gradient descent. Now, this model has achieved a top 5 error rate of 6.67%. But the drawback of these models lies in the difficulty in training these models, and these models generally take a lot of time to train itself. Now we move on to the approach that I have implemented for this current project. This approach can be divided into two phases. Number one is that of an automatic feature extraction and facial key point detection using a 4-layer convolutional neural network. The phase 2 is the actual emotion detection model, which also uses a 4-layered CNN with transfer learning. We have also implemented a 5-fold cross-validation SVM model so that we can compare the results of the SVM and the CNN models and prove that the CNN models are actually a good fit for the classification problem. For the phase 1, we have a data set of 7049 training and 1783 test samples. Now, these are grayscale images of 96 cross 96 dimension, and we also have 15 key points as the labels. Now these 15 key points represents the x and y coordinates on an image, which represents the specific key areas such as that of a nose tip or the corner portion of that of an eyebrow, etc. So here the architecture that we have used is a 4-layer convolutional neural network, and each and every layer is followed by a max pull, dropout, and a ReLU layer. Now this ReLU is basically the rectified linear unit, and we would be explaining each and every layer in detail in the subsequent slides. So after the CNN layers, we also have a dense fully connected layers, and finally we have our output layers, which predicts these 15 key points. Now here are some of the results that we have achieved from the phase 1. So these blue spots actually denotes the key points on the faces. For example, these denotes the nose tip and the right corner of that of an eyebrow. Now these can be used as a feature extractors for our emotion detection models, which we would see in the later slides. Now let us dive into some of the CNN layers and get a hang into what all these layers stands for. The ReLU layer, most important use is its speeding up of the training of a neural network. And the gradient computation is very simple, and it also prevents the problem of vanishing gradient, which is present in a sigmoid units. The second layer is a max pooling layer. Now this max pooling performs a nonlinear downsampling along the dimensions of an input image. Now it partitions the input image into a set of non-overlapping rectangles, and for each subregion it outputs the maximum. The pooling layer serves as progressively to reduce the spatial size of the representation, to reduce the number of parameters and amount of computation that is required in the neural network, and hence it also prevents from overfitting. The last layer is basically the last layer which penalizes the model and also compare the results from the true and the predicted levels. Now for our case, we have actually used a softmax classifier as our final loss layer. Then we have the fully connected layers. Now these layers uses a high level features extracted from the convolutional and the pooling layers, and it also helps in that of a classification purpose. The dropout layer was introduced in neural network to prevent overfitting. At each training stage, the individual nodes are either dropped out of the net with a certain probability or kept in with a certain probability, so that a reduced network is left. The incoming and outgoing edges to a drop node are also removed. Only the reduced network is trained on the data in that stage. Dropout layer also helps in preventing the overfitting of that of a model. Now this is the phase 2 of our complete model structure, and here the data set consists of 35887 grayscale images of 48 cross 48 dimensions. Now to improve the training process of the model and to increase the variability in the training samples, we have actually augmented our training samples and flipped the images along the vertical axis to generate more training samples. The CNN network proposed here is the same as that of the phase 1, with a difference of the output layer, wherein we have used a softmax classifier. And here in each and every stage, instead of using the Glorot style of initialization, which is a default in the lasagna library, we are actually initializing the weights and the biases from the weights that has been learned from the phase 1 model. Now let's learn about the transfer learning and how it is actually helping us to get a better trained model. In practice, very few people train an entire CNN network from scratch because it is relatively rare to have a data set of sufficient size. Instead, it is common to pre-train a convnet on a very large data set and then use that network either as an initialization or as a fixed feature extractor for the task of our interest. So here the transfer learning can be used in basically two different stages. The first one being as a feature extractor, in which the last fully connected layer is removed from the pre-trained model and it is passed across the new data set. The model computes the vector for every image and that contains the activations of the hidden layer immediately before the classifier. And we call these kind of features the CNN codes. These CNN codes are then reload, and once we extract the codes from all these images, we train a linear classifier or the softmax classifier for the new data set. The second strategy calls for replacing the classifier for the new data set and fine-tuning the weights of the pre-trained model by backpropagation. It is possible to fine-tune all the layers of the ConvNet, or it's possible to keep some of the earlier layers fixed and only fine-tune some higher-level portion of that of a network. These are some of the results that we have obtained from a final model, and as you can see here, below each and every image we have the predicted and the actual emotion labels shown, so that we can judge the performance of a classifier. Now let's move straight to the demo section. So here the first model that I would be displaying is the support vector machine. So here an SVM classifier has been created. Now the different kind of parameters that has been provided to this SVM classifier is as follows. The tolerance level has been kept to 0.01 and the kernel that has been used is the RPF, which is a default in the sklearn implementation. Now this kernel has proven good results in various kind of classification, and thus we have used this kernel for our purpose as well. So here the ratio between the training and the test set has been kept to 9:1, and then the model has been trained and has been pickled so that it could be loaded afterwards. And here we run the classifier on the test set, and the results that has been obtained is close to 32%. So that, and the classification results are being displayed here, and the confusion matrix is also laid down here. So as you can see that this classifier is more biased towards one sort of emotion, and this particular column actually denotes the emotion state of happy. So this means that the classifier tends to predict a lot of emotions as happy, and thus the accuracy of this model is just 32%, which can be bettered once we see the other models, that is the CNN models that we will be proposing in a short while. Now let's move on to the next model, that is the CNN based model. So here the this first model is a part of the phase 1 architecture, that is the detection of the key points on the faces. So here we have actually got a training set of close to 7,000 images, and we have applied convolutional neural network on this image data. So here this method actually converts our input images to this form, because this form is required by the CNN network to process these images. So here C represents the channel and the X and Y represents the dimensions of the image. Different architecture for this neural network is as follows. In the beginning we have an input layer wherein we feed the input image, which is of 96 cross 96. Then we have 4 convolutional layers, which has got the number of filters as 64, 128, 512 and 512 respectively. The filter size has been kept constant to be 3 cross 3. After each and every convolutional layer we apply the max pool and the dropout layers. The max pooling size has been kept to 2 cross 2, and the dropouts tends to increase as the number of filters increases. So in the first filter it's only 10%, followed by 20% and 30%. Now the output number of units is actually 30. This 30 represents the points that this model is predicting. For example, the X and the Y coordinates for the 15 key facial points is being detected, and it's actually a regression type of problem. So here the learning rate we have used is 0.01. Moreover, after the convolutional layers, we also have 2 hidden layers. These are fully connected layers having 256 and 512 neurons each. We have trained the model for 1000 epochs, And all of these models have been trained on AWS servers with the CUDA support. Now, once the model has been trained, it has been loaded back for our purpose. And here we are actually predicting and showing up the results that we have obtained after the model has been trained. So as you can see here, this represents the 50 test samples and the results that we are getting for these 50 samples. So we can also run it for the other 50 samples as well, just to see how the results are coming. So these features learned from this model has been used as in the form of transfer learning for our emotion detection model, which we will see shortly. So here all these key points has been learned by the model and which will be used later in the other model as well. So as you can see, the accuracy that we are getting in this particular model is quite good. And due to the data augmentation that we had applied, the images which have slight variations can also be detected through this model. Now let's move on to the last model, that is the emotion detection model. So here the architecture of the model is kept same as the previous model. The reason being that we are applying the concept of transfer learning, and we would be initializing the weights of each and every layers for this model with the weights learned from the previous model. So this line of code actually initializes the weights of the different convolutional layers with the weights from the previous model's convolutional layers. So here the number of filters and the filter sizes all has been kept the same as the previous model, but the main difference between this model and the previous model is in the learning rate, and most important being the output layer. So here the output layer is basically a softmax classifier which is classifying our results into 7 different classes. So the earlier model was a regression based model, so this is a classifier. Now once this model has been trained, so as you can see the model has been trained in AWS servers, and we have pickled these models into this name which we are loading back for prediction purpose. So the accuracy that we are getting from this model is close to 60%. And here this particular diagram represents the confusion matrix, and here the confusion matrix in the numerical form. So as you can see, the diagonal elements are the correct predictions by the model, and the other numbers denotes the false positives and the false negatives for this particular model. So here the final results, as you can see, is this. Like this displays the first 50 images, and this y-axis label actually denotes the actual emotions, and the x-axis label denotes the predicted emotion for this particular image. One point I would like to mention here is that there are certain emotions such as neutral and sad, which are also not easily distinguishable by humans. So the algorithm tends to make a lot of mistakes for these kind of emotions, and the result of which our accuracy has gone down to 60%. So the 60% accuracy in this particular data set is quite good, since the data set only has a dimension of 48 cross 48 and has a lot of pixelations and a noise present in the images which needs to be pre-processed. And the results that we are getting is as follows. So let's run it for a different set of 50 images, for example this. So the results will be coming up in a short while. So we have actually used lasagna for our training purposes. This is a deep learning library which is built on top of Theano, and this is a lightweight library and used for the deep learning purposes. So as you can see, these are the next 50 set of images and the prediction values. So fairly we are getting accurate results for all these images, which seems to be pointing out that the classifier is working properly. Now let's move on to some of the evaluation results of the models that we have created. For the phase 1, the RMSE score of the model was 1.78. For phase 2, the accuracy of the different models has been listed down in the table. SPM had an accuracy of 32%. The CNN with no data augmentation had an accuracy of just 46%. When we had applied the data augmentation, then the accuracy increased to 55%. And the last model of ours, which involved transfer learning as well as data augmentation, had an accuracy of 60%. Thing to note here is that this last model also converged in just 50 epochs. So the model was trained much faster as compared to the previous one. Now these are some of the results from the state-of-art models that we have discussed earlier. So the Google Net, which is a 27-layer CNN model, had an accuracy of 91%, and the SPM with a 10-fold cross-validation along with a certain amount of data pre-processing. So they achieved an accuracy of 87%. Finally, the data set that is the FIR 2013 data set that we used for our project was relatively a tougher data set since it has just a resolution of 48 cross 48, and there was a lot of inherent noise present in the data. Now the accuracy of the CNN model achieved from the FIR 2013 data set is quite close to human accuracy, and the winners of the competition actually obtained an accuracy of just 64%, and our model also was able to achieve accuracy of 60%. And the results that we have shown prove that the use of transfer learning can help achieve better results in these kind of problems.